Welcome back to the deep dive. If you are building a modern AI system, whether it's, training a massive large language model or setting up a really high precision retrieval augmented generation RAG system, you inevitably hit this invisible roadblock, getting content out of documents properly.
Oh, absolutely. It's like the silent killer of quality in so many projects. Everyone's focused on the big shiny LLM, right?
Right.
But if the data you feed it, maybe it's a complex table from some dense financial report or a really intricate formula from a physics paper, if that gets garbled because the parser just couldn't handle it.
Or the whole system downstream breaks down.
Exactly. The LLM starts hallucinating or it misunderstands. Or maybe the RAG system just fails to pull the right information. It all traces back to that initial extraction step.
And that's precisely the challenge we're digging into today. We're looking at a potentially revolutionary open source solution called MinerU 2.5. It comes from the Shanghai Artificial Intelligence Laboratory. Our mission here is to really understand how this new version, MinerU 2.5, manages to achieve, frankly, state-of-the-art accuracy in document extraction. We're talking performance that rivals the big proprietary players.
And critically, it does this while running on a model that's surprisingly incredibly small and efficient.
Yeah, that efficiency point is key.
It really is. It's a perfect subject for a deep dive because it cuts right to this core dilemma in AI right now, the resource tension. Early LLM, they grew up on web data, which was easy to scrape.
Relatively easy, yeah.
But that well is kind of running dry, or at least the quality is becoming an issue. The really deep specialized knowledge, the academic research, government reports, technical manuals, it's locked away in PDFs, in complex document layouts.
Stuff that standard web scrapers just can't touch.
Exactly. And unlocking that high-value data, that needs sophisticated tools. MinerU 2.5 is basically claiming to be the most precise open-source tool out there for doing just that.
Okay, so let's unpack this. Let's maybe start with a bit of history. If document parsing is so critical, why has it been such a persistent headache? Why wasn't this solved years ago? What makes it so hard?
Well, the fundamental difficulty, really, it boils down to the sheer, almost overwhelming diversity of documents out there. And also how inconsistently information is actually represented within those documents.
Right, because when we say document, that could mean anything.
Exactly. It could be a sparse, two-column academic paper layout, or it could be a super dense, multi-page financial report packed with tiny footnotes and complex tables, or an exam paper, or a textbook with code snippets embedded right next to diagrams and equations.
And each of those types probably breaks a different traditional parsing method, right?
That's precisely it. Every approach has its Achilles heel.
Our sources lay this out pretty clearly. They talk about the limitations of the solutions that existed before, which really set the stage for why the original MinerU project even started. Maybe we can quickly walk through those four traditional pillars they mentioned.
Sure. The first one, probably the simplest conceptually, is OCR-based text extraction.
Optical character recognition, just reading the letters off the page image.
Yeah, essentially the model looks at the page as an image and tries to transcribe the characters it sees. And, it's okay, maybe even fast if the text is super clean, standard font, simple layout.
But the moment things get complicated,
the moment you introduce any real structural complexity, like a table with merged cells or a weird font or especially a complex mathematical formula, OCR starts introducing massive amounts of noise. It's just completely unsuitable if you need high-quality structured data for, say, training an LLM.
Okay, so OCR is out for complex stuff. What's next?
Next up is library-based text parsing. Think of tools like Pymo PDF is a common one.
Yeah. Use that.
Right. And it's fantastic for digitally native PDFs.
Yeah.
Where the text is already encoded as text, not just an image. It's lightning fast. Very accurate for just pulling out plain text blocks.
But there's a big but.
A huge but.
Yeah.
It completely fails on anything embedded that isn't actual text. It basically ignores complex tables. It doesn't see formulas rendered as images. It won't understand diagrams. It's essentially blind to the document's visual structure and non-text elements.
So it gets the words but misses the context, the relationships.
Precisely. Which leads us to the third approach, and this is the one that MinerU 1.0 initially adopted: multi-module document parsing.
Okay, this sounds more sophisticated.
It is. It's basically a pipeline strategy.
Yeah.
The idea is, okay, let's stop trying to make one model do everything. Instead, you use a sequence of specialized models.
So like one model finds the layout first.
Exactly. A layout detection model identifies the bounding boxes. Here's a block of text. Here's a table that looks like a formula. That's an image.
And then it hands off those boxes.
Right. It hands off those specific regions to other specialized models. an OCR model for the text boxes, a table recognition model for the table boxes, a formula recognition model for the formula boxes, and so on. Each component does one thing well.
That sounds pretty robust, actually. Why didn't that just solve the problem?
Well, in theory, it's robust.
Yeah.
But historically, the open source models available in this multi-module category, they often failed that critical diversity test we talked about.
Ah, right. Trained on the easy stuff.
Yeah, they were typically trained heavily on a very narrow slice of data, like academic papers from ArcSev, clean layouts, mostly text and standard math.
And then you throw a messy financial report at them.
And they just fell apart. They performed miserably on real-world documents, which are full of, weird layouts, different kinds of tables, footnotes, watermarks, all sorts of complexity they hadn't seen before.
Okay, so specialization is good, but the specialists need broad training. Got it. What's the fourth pillar?
The fourth one is the really modern, ambitious approach, end-to-end multimodal LLM parsing, or MLLMs.
These are the big do-everything models.
Exactly. They try to unify all these steps, layout, OCR, table recognition, formula parsing, everything into one massive system, usually a vision language model. Conceptually, they're the most advanced.
But it's always a but.
Always a but. They face, well, at least two massive hurdles. First, to work well across diverse documents, they need an absolutely enormous and incredibly diverse data set for training, which is hard to curate and often proprietary.
And the second hurdle?
Inference cost. These models are computationally very demanding. Processing high-resolution document images page by page with a giant MLLM, it's just too slow and expensive for practical large-scale use. You couldn't realistically process millions of documents this way without breaking the bank.
Okay, so that brings us back to MinerU 1.0. They took that multi-module pipeline approach.
Yes, but they made a crucial improvement. Instead of relying on those narrowly trained open source models, they used a suite of models from their own PDF extract kit. And the key difference was that these models were explicitly trained from the start on diverse, real-world document data.
So they tackled the diversity problem head-on within the pipeline framework.
Exactly. They recognized that data diversity was non-negotiable for real-world performance.
So what did that MinerU 1.0 pipeline actually look like?
It was a pretty highly engineered, four-stage process.
Yeah.
And it put a lot of emphasis on careful cleanup and post-processing. Stage one was document preprocessing.
Just basic file handling.
Basic but essential. Filtering out password-protected or encrypted files, checking for obviously garbled content, identifying the language it initially supported, Chinese and English, and crucially, determining if the PDF was scanned or digital.
Because a scanned PDF needs OCR right away.
Right, while a digital one might use library-based methods for some text, potentially, so that detection routes the document down the right path.
Okay, pre-processing done. What's next?
Stage two is the core content parsing. This is where those specialized models, the layout detector, the formula recognizer, the table parser, actually do their work on the document content based on the pre-processing steps.
And then the really important bit, you mentioned post-processing.
Yes, stage three, content post-processing. This is where, honestly, a lot of the magic happened in version 1.0. The raw outputs from the parsing models can still be messy or structurally inconsistent. This stage is all about hammering that output into something that's semantically coherent and reliable for a machine to use downstream.
What kinds of things did they have to fix?
Oh, lots of subtle but critical details. For instance, they had explicit rules baked in to deal with overlap bounding boxes, or B boxes.
What does that mean, like boxes drawn on top of each other?
Yeah, imagine a photo in a report, and there's a caption written directly over the bottom edge of the photo. The layout model might detect a box for the image and a box for the text, and those boxes overlap.
Ah, okay. How do you resolve that?
MinerU 1.0 had rules for this. If one box was completely inside another, like text inside an image region, it would resolve that containment. If they just partially overlapped, it might say, shrink the bounding boxes slightly to make sure each semantic unit, the image, the text was distinct and didn't bleed into the other. It's about preserving the integrity of each element.
That sounds meticulous. What else?
I think maybe the most challenging part, and something people often take for granted, is fixing the reading order.
Oh yeah, multi-column documents must be a nightmare.
Total nightmare. If you just process boxes based on their coordinates, a model might read the top of column 1, then jump to the top of column 2, then back to the second line of column 1. It's chaos.
So MinerU 1.0 had to figure out how humans read.
Essentially, yes. They developed a specific segmentation algorithm that rigorously enforced the standard human reading order, generally top to bottom, then left to right.
That sounds simple, but implementing it.
It's deceptively complex. Think about a textbook page where a single paragraph starts at the bottom of the left column and then continues at the very top of the right column. The algorithm has to correctly identify and link that cross-column jump.
Wow.
Yeah, they actually built rules to enable not just cross-column merging, but even cross-page paragraph merging. If a paragraph breaks across a page boundary, that's absolutely essential if you want to preserve the semantic flow of the text for a downstream LLM.
Makes sense. You can't feed an LLM half a paragraph.
Exactly. And then the final stage of the pipeline was filtering.
Getting rid of the junk.
Pretty much. Removing irrelevant regions like headers, footers, page numbers, maybe even some watermarks or side notes, depending on the configuration. The goal is to give the LLM only the core, semantically rich content of the document body.
And the output format.
Stage 4 was format conversion, typically outputting structured formats like markdown or JSON, which are much easier for downstream systems to ingest.
Okay, so MinerU 1.0 sounds like a really solid, carefully engineered pipeline that solved many of the existing problems, especially around data diversity and post-processing.
It was. It laid a very strong foundation. But, pipelines with multiple specialized components can have latency issues, and integrating everything perfectly is complex. To really push the boundaries and compete directly with the speed and potentially higher accuracy ceiling of end-to-end models, they realized they needed to rethink the core architecture.
They needed to embrace the VLM approach, but somehow sidestep its major drawbacks.
Precisely. They needed the power of a VLM without the crippling computational cost. And that's exactly what the MinerU 2.5 breakthrough delivers.
All right, so this is the big shift. Moving from that complex, multi-stage pipeline we just discussed to a much more streamlined vision language model, a VLM. But as we established, VLMs usually struggle with cost, right? They need high-resolution images to see fine details, but processing those huge images is just computationally brutal. So how did MinerU 2.5, which you said is a small model, get around this fundamental conflict?
Yeah, this really gets to the heart of the VLM dilemma for document parsing. You absolutely need high resolution. Think about seeing small exponents in a formula, or faint lines in a complex table, or fine print in a footnote. You need the pixels.
Makes sense.
But if you just feed a native high-resolution image, maybe something like, say, 2,000 by 3,000 pixels, directly into a standard VLM architecture,
Right.
the number of visual tokens the model has to process just explodes. It scales quadratically, following that ON complexity curve.
Right, the n-squared problem.
Yeah.
Double the image width and height, and you quadruple the compute cost.
Exactly. And the crazy part is, most of that computation is wasted. Think about a typical document page. Huge margins, lots of white space between columns or paragraphs.
Yeah.
You could easily spend like 90% of your expensive GPU cycles analyzing completely blank white space that contains zero useful information.
It's incredibly inefficient.
Terribly inefficient.
Except.
So MinerU 2.5 tackles this head-on with its key innovation, which they call decoupled two-stage parsing.
Decoupled, meaning they separate parts of the process?
Precisely. They have this core insight. You don't actually need high resolution for everything on the page simultaneously. You only need high resolution for the specific content regions when you're trying to recognize them.
Okay, so break down these two stages for us. Stage I is the core stage.
Stage I is layout analysis, and yes, you can think of it as the core stage. Here's how it works. The input document image is first rapidly resized down to a small thumbnail. The paper specifies 1036 by 136 pixels.
So much smaller, much faster to process.
Exactly. The goal here is pure efficiency and getting a holistic global understanding of the page structure. This relatively lightweight 1.2 billion parameter VLM processes this small thumbnail very quickly.
And what does it figure out from the thumbnail?
It figures out the overall map of the page. Where are the columns? Where are the approximate bounding boxes for text blocks, figures, tables, formulas? It's basically generating the coordinates, the high-level structure. And because the input resolution is so low, the computational cost is minimal.
Right, it processes the whole page, including all that white space, but it does it cheaply at low resolution. This gives it the coordinates.
Which then guides stage 2. This low-resolution layout map becomes the input for stage 2. Content recognition, which is the fine stage.
And this is where the high-resolution magic happens.
Yes, but without the crippling high-resolution cost. Guided by those precise coordinates identified in stage 1, the model does something clever. It intelligently crops out only the key regions, the detected bounding boxes for text, tables, formulas, directly from the original native high-resolution image.
Ah, I see. So if a complex table only takes up, say, 10% of the page area,
the model only processes that specific 10% region at maximum detail. The paper mentions up to 2048 tokens. derived from high-res patches like 28 by 28 pixels within that region. This preserves every crucial visual detail needed for accurate recognition, the small fonts, the lines, the symbols.
And it completely avoids processing the other 90% of the page, the margins, the white space at high resolution.
Exactly. It completely bypasses that quadratic cost associated with scanning the entire high-res page. It's a really brilliant piece of engineering.
That makes a lot of sense. What are the other benefits of this decoupled approach?
Well, besides the huge reduction in computational cost, it also really helps with interpretability. You can clearly see which parts of the page the model focused on for recognizing specific content.
You can trace the process better.
Right. And maybe even more importantly, by focusing only on the relevant content regions at high resolution, it significantly mitigates the risk of VLM hallucination. Larger models processing the whole page, especially long documents, can sometimes get confused or start guessing content in low information or noisy areas, or misinterpreting things seen at low effective resolution. By cropping and focusing, MinerU 2.5 processes smaller, cleaner, high-fidelity patches, reducing the chances of it making things up.
Okay, I have to pause you there because this is pretty striking. You mentioned earlier the model size is only 1.2 billion parameters.
That's right. It's a combination of a Quinn2Instruct 0.5b language model as the decoder and a 675 million parameter Navit vision encoder. So 1.2b total.
How is it even possible that a 1.2 billion parameter model is reportedly outperforming massive competitors? We're talking about models like Google's Gemini 2.5 Pro or other open source giants that are tens, even hundreds of billions of parameters in size.
Yeah, it's counterintuitive, isn't it?
It really is. Does it just suggest that the bigger models were doing something fundamentally wrong, like their training or their inference strategy was just massively inefficient?
I think it suggests a couple of things. First, it underscores that efficiency isn't just about raw parameter count. It's about how you use those parameters.
Well,
Intelligent token usage matters. MinerU 2.5 is incredibly frugal. It only processes the visual tokens that actually contain content information, while the bigger models might be drowning in redundant tokens from white space when processing the full page.
so smarter architecture beats brute force size to some extent.
To a large extent here, it seems. But the second key factor, and we absolutely have to get into this next, is the data and the task formulation. The architecture is clever, but the performance also comes from extremely high-quality training data and rethinking how the model tackles specific tasks like table or formula recognition.
Okay, so it's not just the decoupled architecture, it's also what they fed it and how they trained it.
Exactly. MinerU 2.5 isn't trying to brute force the problem with scale. It's solving it more elegantly by combining this efficient architecture with very smart data strategies.
And you mentioned this elegance translates directly into speed, making it practical for real-world, large-scale jobs.
Absolutely. The sources give some concrete numbers here, which really highlight the efficiency point. They benchmarked MinerU 2.5, achieving an end-to-end throughput of 2.12 pages per second on their hardware.
2.12 pages a second. How does that compare?
Well, they compared it to other models. It apparently outperforms Monkey OCR Pro, which is a 3 billion parameter model, by about 4 times. And it beats another system called Dots.OCR by 7 times.
Wow, okay. That's a significant speed up.
It really is. And it shows they're serious about production use. They even mentioned switching their acceleration framework from Sklang to VLLM. For listeners who work with deploying LLMs, you'll know VLLM is a key library for achieving high-throughput inference serving. That switch signals they're optimizing for speed at scale.
Okay, so we've got the clever architecture delivering speed and efficiency. Now, let's pivot to that other crucial piece you mentioned, accuracy. How did this relatively small model get so good? It must be down to the training data and the training process itself.
You absolutely nailed it. The state-of-the-art performance isn't just a fluke of the architecture. It's deeply rooted in what they call a systematic data engine. This engine was specifically designed to tackle the classic problems that plague real-world datasets: noise, imbalance, and, crucially, inconsistent annotations.
So this data engine is how they managed to teach the relatively small 1.2b parameter model to understand these incredibly complex and diverse document structures.
Precisely. It's about maximizing the quality and the learning potential of every single data point they used.
Okay, let's start at the beginning of that process. Data curation and pre-training. You mentioned earlier they needed to avoid the common bias towards just academic papers.
Right. Their curation process was much more structured than usual. They actively filtered and balanced their raw data across 4 key dimensions. First, layout diversity. They actually used visual clustering techniques to ensure they captured a wide range of different page styles and structures.
Okay, what else?
Second, document type diversity. They made sure they had a good mix, not just academic papers, but also complex financial reports, PowerPoint slides or notes, textbooks, exam papers, things like that. Real-world stuff.
Their dimension.
Element balance. They actively monitored the data set to ensure it contained a sufficient number of examples for all the tricky elements. Not just text, but also formulas, complex tables, figures, charts, diagrams.
In fourth.
Language balance, ensuring good coverage of both Chinese and English documents, as those were their initial target languages. So the goal was a data set that truly reflected the messy reality of documents, not just the clean corner cases.
And they didn't just collect this diverse data. You mentioned they actually refined the annotations using other larger models. That sounds like a serious quality control step.
It's a really intensive, almost industrial strength approach to quality control. Think of it like this. Before they even started training the small 1.2B MinerU 2.5 model, they wanted to generate the best possible ground truth annotations for their training data.
So they used expert models to check the labels.
Exactly. They used a massive, state-of-the-art Qwen 2.5 VL72B model. That's a 72 billion parameter, multimodal model, specifically to verify and correct the text recognition results in their dataset.
Okay.
For formulas, they use a model called UnimerNet, which they retrained for high-fidelity formula recognition. And for table structures, they used a specialized in-house model.
So they're essentially using larger expert models to create near-perfect labels for training the smaller, more efficient model.
That's the idea. This pre-training data refinement ensures that the image annotation pairs used to teach MinerU 2.5 were as close to pristine as possible. It gives the smaller model a much higher quality signal to learn from compared to just using raw, potentially noisy human-labeled data.
That makes a lot of sense. Invest heavily in data quality up front.
Now, what about this other thing you mentioned, iterative mining via inference consistency, or IMIC? That sounded really interesting, almost like the model helps improve itself. Yeah, ISE is probably the most novel part of their data strategy, and it's focused on the fine-tuning stage after the initial pre-training. It's a really clever way to make human labeling effort far more efficient.
How does it work? Instead of just labeling random documents.
Right. Instead of randomly sampling data and having humans label it, where you might waste a lot of time labeling easy examples, the model already gets right. IMAC automatically identifies the hard cases, and it does this by cleverly using the model's own uncertainty.
Uncertainty, measured by how consistent its answers are.
Exactly. They measure its inference consistency. Here's the process. They take an unlabeled data sample and run it through the current MinerU 2.5 model multiple times using stochastic inference.
Stochastic meaning, with some randomness introduced.
Yeah, techniques like dropout are inherently stochastic. Running inference multiple times with slightly different internal states simulates variability. If the model is really confident about, say, the structure of a table on that page, all 5 or 10 stochastic runs will likely produce the exact same output structure.
It's stable.
Very stable. But if the model's uncertain, maybe the table has weird borders or the formula is ambiguous, those different stochastic runs might produce slightly different outputs. The recognized structure might change slightly each time.
Ah, okay. And they measure that difference using those specific metrics you mentioned.
Precisely. They use task-specific metrics to quantify the inconsistency or divergence between the outputs of the stochastic runs. For layout, they use that page IOU metric we'll talk more about. For formulas, they use CDM, which stands for character level definition metric, basically how accurate the recognized formula string is. And for tables, they use TEDS, the tree edit distance score, which measures structural similarity.
So if the scores vary a lot across the different runs?
If the inconsistency crosses a certain predefined threshold, that sample gets flagged. It's marked as a hard case, an example that lies near the model's current decision boundary, something it's clearly struggling with.
And only those hard cases get sent for human review.
Exactly. Only these maximally informative, difficult samples are presented to human experts for careful review, correction, and annotation. This strategy maximizes the value extracted from expensive human labor. You're focusing effort precisely where the model needs the most help. It drives performance improvements much faster than just labeling random data.
That's incredibly smart. It's like targeted tutoring for the AI model.
It really is a very efficient feedback loop.
Okay, so amazing data strategy. But MinerU 2.5 didn't just rely on better data. They also fundamentally rethought how the model should even approach some of these core document understanding tasks. Let's dive into that task reformulation. Maybe start with layout analysis.
Right. They made some significant changes here compared to traditional approaches. First, they moved to a system of unified tagging with much broader scope.
What does unified tagging mean here?
It means having a single, consistent set of tags for everything on the page, aiming for two things: comprehensive coverage and fine granularity.
Comprehensive coverage, meaning tagging stuff beyond just the main text.
Yes, including non-body elements like headers, footers, page numbers, even page-level footnotes. Now, you might think, why tag stuff you often want to filter out later?
Yeah, exactly.
Because for a RAG system, for instance, explicitly recognizing these elements is crucial so you can reliably filter them later. You need to know what's header-footer noise versus main content.
Okay, that makes sense. And fine granularity.
This means giving distinct tags to elements that might have been lumped together before. For example, recognizing not just text block, but distinguishing between regular paragraphs, lists, bulleted or numbered, algorithms, and code blocks. Each gets its own specific tag.
Why is that level of detail important?
Because it provides much richer semantic information downstream. An LLM needs to understand the function of a piece of content. This is code. This is a list item, not just its location on the page. This fine-grained tagging preserves that crucial semantic distinction.
Got it. And they also changed the prediction process itself. You mentioned an enhanced paradigm.
Yes. Instead of just predicting bounding box coordinates and class labels separately, the new layout analysis paradigm in MinerU 2.5 predicts 4 things simultaneously for each detected element: its position, bounding box, its class, paragraph, table, formula, list, etc., its rotation angle, and its reading order index.
Predicting the rotation angle right away seems useful. Lots of scanned documents have skewed text.
Exactly. It resolved the problem of rotated or skewed elements immediately, rather than having to correct for it later. But predicting the reading order index simultaneously with the position and class is also really powerful. It helps streamline the whole process of reconstructing the document flow correctly.
Okay, now let's talk about that metric you mentioned for layout. Page IU. You said the traditional metric, MAP, mean average precision, often failed for document layouts. Why was MAP problematic?
The core issue with MAP in this context is its reliance on intersection over union IOU thresholds between the predicted bounding boxes and the ground truth bounding boxes. This sounds reasonable, but it can lead to situations where a visually superior prediction gets penalized.
Can you give us that visual example again? It really clarified the issue.
Sure. Imagine you have a paragraph of text. Let's say the ground truth annotation is just one big coarse bounding box drawn around the entire paragraph.
Okay.
Now, Model A predicts a layout that matches this perfectly one big coarse box. It gets a great IOU score, maybe 1.0, contributing positively to its MAP.
Seems good.
Now, consider Model B. It analyzes the same paragraph but predicts 5 precise individual bounding boxes, one perfectly fitting each line of text within the paragraph.
That sounds much more useful for actual text extraction.
It absolutely is. Structurally, it's a far superior prediction for downstream tasks. But here's the problem. None of those 5 small, precise boxes will have a high IOU score when compared against a single large ground truth box. They only cover a fraction of its area individually.
So Model B, despite giving a much better, more granular result, gets heavily penalized by the MAP metric.
Exactly. It might score much lower on MAP than the model that just drew a lazy coarse box. The metric was fundamentally misaligned with what constitutes a good layout prediction for document analysis. It was punishing the very precision we needed.
So how does Page IU fix this?
Page IU takes a different approach. Instead of comparing individual boxes, it measures the overall page-level coverage consistency. It basically creates a pixel mask or map representing the area covered by all the predicted boxes, and another map for the area covered by all the ground truth boxes. Then it measures the spatial overlap consistency between these two entire maps.
So it looks at the total area covered correctly, regardless of how the boxes are drawn.
Essentially, yes. It cares about whether the predicted layout accurately covers the same page regions as the ground truth in aggregate. The paper gives an example where a visually poor prediction, like the single coarse box, might get a misleadingly okay score like 0.78 with traditional metrics, while the visually superior fine-grained prediction, the line-by-line boxes, correctly achieved a much higher score of 0.97 using Page IU.
So it aligns the quantitative score much better with human visual perception and the actual goal of structured extraction.
Precisely. It's a metric designed for the task.
Okay, fascinating. Let's shift gears now to the actual content extraction, starting with formula recognition. Formulas are notoriously difficult. They're like a mix of text symbols and 2D visual structure. How did MinerU 2.5 tackle the common problem of structural hallucination in complex math?
Yeah, formulas are tough. The standard failure mode, especially with long or multi-line equations, is what they call structural hallucination. The model tries to parse the whole complex thing as one entity and just messes up the structure. Maybe it mislines exponents, confuses subscripts, or breaks the logical flow of a derivation.
So MinerU 2.5 uses this atomic decomposition and recombination ADR strategy to prevent that.
Exactly. The core idea of ADR is to stop trying to parse complex formulas in one go. Instead, it first classifies formulas into two types based on their semantic structure: atomic formulas and compound formulas.
What's the difference?
An atomic formula is the smallest semantically indivisible unit. Think of a single equation line, like EMCSA. A compound formula is an ordered set of these atomic formulas that belong together structurally. The classic example is a multi-line derivation where each line is an atomic formula, but they need to be grouped and aligned.
Okay, so it breaks down the compound ones first.
Yes. Step one is using the layout analysis, which now understands fine granularity, to decompose the compound formula into its constituent atomic lines or units. Find the bounding boxes for each individual line.
Then process each line separately.
Right. Step two is that MinerU 2.5 recognizes each atomic line individually, converting just that single line into its latex representation. This is a much simpler task than parsing the whole multi-line structure at once.
And the final step is putting them back together.
Right.
Recombination.
Exactly. Step three is structural recombination. Using the positional information, the coordinates of the atomic lines from the layout analysis, the system intelligently recombines the individually recognized latex strings into the correct overall structure.
So for that multi-line derivation example,
It would recognize each line's latex and then use their vertical alignment and positioning to wrap them correctly in, say, a latex-aligned environment. This is crucial for mathematicians, as align ensures things like the equal signs line up perfectly across multiple steps. By decomposing first and then recombining structurally, ADR effectively prevents those structural hallucinations and preserves the formula's logical integrity.
that sounds incredibly important for any system trying to actually understand or use mathematical content, not just display it.
Absolutely critical.
Okay, last major reformulation area, table recognition. Tables are maybe the biggest pain point for our beat systems. They're everywhere, they're complex, and getting the structure wrong completely destroys the data. What was MinerU 2.5's innovation here?
Their main innovation was moving away from directly generating raw HTML sequences to represent the table structure.
Why is HTML bad for this? It seems like the standard way to represent tables.
It is standard for web display, but for a VLM generating the structure, HTML is actually quite problematic. It's syntactically very heavy. You have all these tags table, TRIDD, TR, plus attributes like colspan and rowspan for merged cells. The sources mention there can be 28 or even more unique structural tokens involved.
That sounds like a long and complex sequence for a model to generate perfectly.
It is, and VLMs, especially smaller ones, can easily get tripped up generating these long, syntactically complex sequences, particularly for large tables with many rows, columns, and merged cells. It's just very prone to errors, missing tags, incorrect nesting, wrong attributes.
So what's the alternative they came up with?
They developed and used an intermediate representation they call Optimized Table Structure Language, OTSL.
OTSL, a simpler language just for tables.
Exactly. It's designed to be fundamentally minimalist while still capturing all the necessary structural information. It achieves two major efficiency gains compared to HTML.
Okay, what are they?
First, it drastically reduces the number of unique structural tokens the model needs to learn and generate. They got it down from 28 plus for HTML to just 5 core structural tokens in OTSL.
Wow, only 5 tokens to represent any table structure.
Apparently so.
And second, this minimalism means the overall sequence length needed to describe a given table is significantly shorter. The paper claims about 50% shorter on average compared to the equivalent HTML representation.
So fewer types of tokens and much shorter sequences to generate. That sounds much easier for the VLM.
Much, much easier, and therefore far more robust. Because the generation task is simpler, the model makes fewer errors. They specifically mention that using OTSL allows MinerU 2.5 to reliably handle really challenging real-world cases that often break HTML-based generators. Things like rotated tables, tables with no visible borders where structure is implied by alignment, and tables with irregular merged cells spanning multiple rows or columns.
That's another great example of tailoring the task output to fit the strengths and weaknesses of the VLM architecture itself.
Absolutely, it's smart engineering. Okay, so pulling this section together, MinerU 2.5's accuracy doesn't just come from the clever decoupled VLM architecture. It's equally, maybe even more so, driven by this incredibly sophisticated data engine using IMIC for smart fine-tuning, and these fundamental task reformulations using page IOU for better layout evaluation, ADR for preserving formula integrity, and OTSL for robust table parsing. It's really an integrated system where all these pieces work together.
That's the perfect summary. It's the convergence of efficient architecture, intelligent data handling, and task-specific optimizations that unlocks this level of performance.
All right, so we've talked about the architecture, the data, the task redesigns. Now let's get to the payoff. How well does MinerU 2.5 actually perform? The proof is always in the benchmarks, right?
Indeed. And they tested MinerU 2.5 extensively on a benchmark suite called Omnidoc Bench. This isn't just any benchmark. It was specifically designed to evaluate document parsing models across a really wide range of diverse, real-world document types, precisely the kind of challenging data we've been discussing.
And the results. How did MinerU 2.5 stack up against the competition, especially those big proprietary models?
The results are frankly quite remarkable, especially given the model's small size. MinerU 2.5 achieved an overall score of 90.67 on Omnidoc Bench.
90.67. How good is that in context?
It's extremely good. To give you some context from the source material, this score actually surpasses top-tier proprietary models mentioned in their comparisons, like Google's Gemini 2.5 Pro, which scored 88.03.
Wait, it beat Gemini Pro? The 1.2 billion parameter model beat Gemini?
According to their results on this benchmark, yes. And it also significantly outperformed larger open-source multimodal models like Qwen 2.5 VL72B, which scored 87.02, and Intern VL 3.524-1B at 82.67.
Wow. So the small, efficient open source model is actually the performance leader on this comprehensive benchmark. That's a huge statement.
It really is. It validates their entire approach. The decoupled architecture, the data engine, the task reformulations. It shows that smart design can potentially overcome brute force scale.
Okay, let's break down that overall score a bit. How did it do on the specific tasks? Let's start with text recognition.
For text recognition, they achieved the lowest edit distance among the compared models, getting a score of 0.047.
Edit distance.
Yeah.
Lower is better, right? It means fewer errors.
Exactly. A lower edit distance means fewer character insertions, deletions, or substitutions are needed to match the ground truth. So 0.047 indicates extremely high fidelity in transcribing text, even when dealing with dense pages or small fonts.
Okay, very accurate text. What about formula recognition? We talked about the ADR strategy. Did it pay off?
It certainly seems so. They measured formula recognition using that CDM metric, character level definition metric, which captures the structural correctness. MinerU 2.5 achieved a leading score of 88.46.
And that high score is likely thanks to ADR handling those complex structures.
That's the direct claim, yes. That score reflects its ability to handle complex, multi-line, and hybrid formulas accurately. They specifically mention achieving state-of-the-art results on very difficult formula benchmark subsets, like the old scans math and ArcSIF math categories within another benchmark called Olmo CR Bench. So it excels even on challenging, degraded, or highly complex mathematical notation.
Impressive. And finally, table recognition. We discussed OTSL and the focus on diverse data like financial reports. How did it fare on tables?
It came out on top there as well. Measured by TEDS, Tree Edit Distance Score, which assesses the accuracy of the parsed table structure, MinerU 2.5 achieved the highest scores, reaching 88.22.
And TEDS higher is better, meaning the predicted structure is closer to the ground truth.
Correct. A high TED score indicates extremely accurate parsing of rows, columns, cells, and importantly, those tricky merged cells. They specifically credit this performance to training on diverse table types, including complex financial documents, noting they achieve SOTA results on benchmarks like FinTapNet, which is focused on financial tables.
So across the board, text, formulas, tables, it's hitting SOTA or near SOTA performance, beating models many times its size.
That's what the benchmark results strongly suggest.
And does this high performance hold up across different types of documents? Or does it still have weaknesses?
That's a key point. Robustness across document types. The benchmark results indicate it does perform very well across the board. They specifically highlight that it excels in categories where other models often struggle.
Like what?
For example, textbooks. They achieved a very low edit distance of 0.0499 on textbook data, which can be complex with mixed content types. Also newspapers, another tricky format with dense columns and varied layouts, where they scored 0.0540 on edit distance.
And qualitatively? Beyond the numbers.
Qualitatively, users and the researchers report superior performance when parsing pages with really complex layouts, maybe alternating blocks of text and images, and also on pages that feature distracting elements like watermarks where other models might miss content or have their detection thrown off. It seems generally more robust to real-world visual complexity.
Okay, this is all very compelling technically, but let's bring it back to the practical level. Why should someone listening, maybe someone building an AI application or working with large document sets, why should they really care that MinerU 2.5 is so good at essentially reading PDFs? What's the real-world impact?
It boils down to the significance for downstream AI. Think about the two big use cases we started with, LLM training and RA systems.
Right. Let's take LLM training first.
If you're pre-training a specialized LLM, maybe you want to build a model that's an expert in legal analysis or financial forecasting or medical research you need to feed it vast amounts of high-quality structured data from documents in that domain.
And if your document parser is bad?
You feed the LM garbage, garbled text, broken tables, misunderstood formulas. MinerU 2.5, with its high accuracy, ensures that the specialized knowledge locked in those expert documents is transformed correctly into machine-digestible formats. It means the resulting LLM is built on a much more reliable, accurate foundation of knowledge from the start. Better input data leads to a better model.
Makes sense. Quality in, quality out. And what about for AGI systems? This seems even more direct.
For AGI, the impact is immediate and critical. RAG systems work by retrieving relevant chunks of information from a knowledge base, often built from documents, to help an LLM generate accurate, grounded answers.
The accuracy of the retrieved chunk is paramount.
Absolutely. If the document parser used to create that knowledge base was inaccurate, the RAG system indexes erroneous or incomplete data. When the system retrieves a chunk to answer a user's question, it might retrieve nonsense, a broken table, a misread formula, text from the wrong section.
Which leads to the LLM giving wrong or nonsensical answers, even if the LLM itself is powerful.
Exactly. A RAG failure often starts at the data ingestion level. MinerU 2.5, by accurately preserving the semantic integrity of the text, the layout structure, the table data, thanks to OTSL, and the formula details, thanks to ADR, directly addresses these failure points at the source. It ensures the context chunks being indexed and retrieved are reliable and accurate.
So it significantly reduces the risk of the RA system hallucinating or providing incorrect information simply because the underlying source data was parsed badly.
Precisely. It turns those messy, unstructured documents into clean, structured, reliable context chunks that the RA system can actually depend on. It's foundational for building trustworthy RAG applications. #outro.
Okay, so let's try to synthesize this deep dive. MinerU 2.5 really seems to have shifted the conversation around document parsing. They looked at the old approaches, the complex multi-module pipelines that were maybe robust but slow, and the big end-to-end VLMs that were powerful but way too computationally expensive.
Right, they saw the limitations of both.
And their solution, this decoupled two-stage VLM architecture, cleverly resolved that core performance versus cost trade-off. It allows a surprisingly lightweight 1.2 billion parameter model to achieve state-of-the-art accuracy that, based on the benchmarks, rivals or even beats competitors that are orders of magnitude larger.
Yeah, the architectural innovation is key. But the true ingenuity, I think, lies in the combination of that architecture with the underlying engineering that supports it.
You mean the data engine and the task reformulations?
Exactly. That sophisticated data engine, using IMC, to intelligently focus human effort on the hardest cases during fine-tuning. And those clever task reformulations, using page IOU to properly measure complex layout accuracy, using ADR to maintain the integrity of mathematical formulas, and using OTSL for really robust and efficient table structure parsing.
It's not just one silver bullet. It's an integrated system.
It's an elegant, highly efficient, and apparently exceptionally powerful system. And crucially, it seems built with industrial-scale processing in mind, given the focus on throughput.
This brings us to our final provocative thought for you, our listeners, to mull over. We've established that the vast majority of deep, specialized human knowledge, scientific discoveries, legal history, financial data, technical specs, it exists locked away in documents, not freely floating on the open web.
Yeah, it's true. The libraries, the archives, the corporate servers.
And we know that AI systems, particularly RG systems aiming for factual accuracy, are fundamentally limited by the quality of the data they can access and understand. LLMs are only as good as the data they learn from.
Garbage in, garbage out, as we said.
So now that we have tools emerging, highly accurate, highly efficient, and importantly, open source tools like MinerU 2.5 that can potentially unlock this vast storehouse of documented knowledge, instantly and reliably structuring it for machines. Here's the question. What is the ultimate ceiling for LLM capabilities if every piece of documentary evidence, every textbook, every report, every datasheet can be instantly and perfectly transformed into reliable, structured data?
That's a fascinating question. It suggests the next really big leap in AI performance might not come just from building even bigger models.
But from finally cracking the code on perfectly ingesting and understanding the existing corpus of human knowledge, getting the foundation right.
Document parsing is the unsung hero, the critical foundation for the next wave of AI. It's a powerful thought.
Definitely something to think about.
And for anyone whose interest is piqued and wants to explore this further or even use it, it's worth repeating that MinerU 2.5 is open source. The project details, the code, the models, they're available on platforms like GitHub and Hugging Face Model Scope.
So the community can actually build upon this work.
Exactly. They can test it, contribute to it, and integrate this high-accuracy foundation into their own applications.
We definitely encourage you to check out the links in the source material for this deep dive, including the detailed benchmark results. That's all the time we have for this deep dive. Thanks for joining us. We'll catch you next time.